Okay, so next let us continue talking about your exam problems. The problem number 4 presented here may be the most difficult one among the in total 8 problems. And according to my observation, only 2 or 3 of you have just solved it in your exam. And actually, this problem has appeared in your textbook, but the solution provided by the textbook is quite lengthy and hard to remember. I guess that most of you just try to recall what is written on the textbook, but instead of solving it by yourself. So here, I would like to provide short but elegant proof that came up when I was grading your exam sheets. Okay, so the problem states the following thing. Let V be an odd-dimensional vector space over the field of real numbers, and T and S be 2 linear transformations which commute with each other. The goal is to prove that the 2 linear transformations T and S share a common eigenvector. Okay. So roughly speaking, my idea is to find a common eigenvector in a subspace of the whole space V. Okay. So we may imagine there are some canonical subspace that may occur in this process, say the kernel of T or the image of T, which is both invariant under T and S, since these 2 operators commute. And to descend our problem to these common invariant subspaces, we need to do some induction on the dimension of this vector space V. So let us do induction on, let us say, n equals dimension of V. Okay. For example, when n equals 0 or 1, the statement is clear. Okay. Since, okay, if V is just the 0 space, then nothing needs to be proved here. And if V is just one real line, then T and S are 2 scalars on this line. So necessarily they share a common eigenvector. We just need to take any non-zero vector along this line. Okay. So let's assume that. Okay, let's assume n greater or equal to 3 is an odd number. So the main idea is to find invariant subspaces, both invariant on the T and S. Maybe we may take, for example, and to do this, we need to assume to consider some trivial cases first. Okay. Say, for example, if T equals 0, then we only need to consider S. Since any non-zero vector, there will be an eigenvector T. So since the dimension is odd, there exists a real eigenvalue of S, which corresponds to an eigenvector. Say C R with an eigenvector V is that SV equals C of V. So you may take this V to be the common eigenvector of T and S. And the existence of this real eigenvalue of S is due to the reason that the dimension of the vector space is odd. Okay. Now, if T is invertible, then I would like to claim that we may assume that T is actually not invertible, since let's just take any eigenvalue of T lies in the sigma of T intersect with the field of the real numbers. Then consider T tilde defined to be T minus the scalar by C. So here C, the tilde of C is not invertible. And Ts share a common eigenvector if and only if T tilde and S share a common eigenvector. Okay. Since the eigenvalues of T is just a C translate of eigenvalues of T tilde. So the rest of the cases, in the rest of cases, we may just assume that T is not zero and is not invertible. Without loss of generality. Okay. So, what convenience these conditions brings up to us? Okay. Then follow that if we consider the kernel of T, then since it is not invertible, then the kernel of T will be a non-zero subspace. And since it is not zero, T is not zero, then the kernel of T will be a proper subspace of V. Okay. And the same reason applies to the image of T. Yeah. So, and these two non-trivial subspaces has the sum of dimension equals to n. By the dimension formula. So, in particular, this implies that either kernel of T or image of T has all dimensions. And its odd dimension is strictly smaller than that of V. So we may, by inductive hypothesis, we may find a common eigenvector of T and S when restricted to either kernel of T or image of T. Restricted to a W and S where kernel of T or so by induction the proof is complete. Do you have any questions about it?
What do we consider about kernel T or an image of T?
Yeah, that's a nice question.
Yeah.
So Wolfgang just asked why the kernel of T and image of T naturally appears here. Yeah. So the first reason I would like to mention here is that the kernel of a linear transformation or the image of it are the natural objects that are invariant under any linear transformation which commute with T. Yeah. So this is the basic reason that we choose these two subspaces. And also I would like to remind you of another reason, but that will be a little bit complicated. So I will put it as a final exercise in this topic. Okay. So this is a simple solution to this problem number 4. And I would like to give you some background of this problem. This is about the property called simultaneously diagonalizable or simultaneously upper triangularizable. Because we will need this proposition. Now, let F be any field and V be a finite dimensional vector space over this field F. And fancy A to be any family inside the vector spaces of linear transformations on V. Okay. Then we would like to consider when the linear transformations in this collection fancy A are simultaneously diagonalizable or simultaneously upper triangularizable. Okay. First, let's put it simply. Fancy A is simultaneously diagonalizable if and only if this fancy A is a commuting family, which means that every two linear transformations in fancy A commute with each other, and each linear transformation in fancy A is diagonalizable. Of course, here all diagonalizable or upper triangularizable over the fixed field F. Okay. And the second statement is that the family fancy A is simultaneously upper triangularizable. If and only if, here we only have the if part. Okay. If fancy A is a commuting family, and each one in fancy A is upper triangularizable. Okay. So we may see this as a basic background of the problem number 4. Okay. So, I would like to say that, okay, let us prove these two statements simultaneously. And first, I would like to make sure that the only if direction of A is trivial. Since if you have a simultaneously diagonalizable family of linear transformations fancy A, then of course each one in this family is diagonalizable. And since they can be simultaneously put into a diagonal form, so you know that diagonal matrix commute with each other. So of course this family also commute with each other. All we need to prove is the converse direction, say the if direction of 1 and 2. Okay, so let us assume that this fancy A is a commuting family. And we also start from some trivial cases. So, for example, if this fancy A consists of scalars, and of course, you know that scalar matrices are represented by diagonal matrix. So, of course, and each subspace of V will be invariant under each element, each linear transformation in fancy A. So it is trivial to find a basis under which this family is simultaneous and diagonalizable. Then, right. So now, if there exists some linear transformation T0 in the family fancy A, which is not a scalar. Then it just means that, okay, over the algebraic closure of this fixed field F, this T0 will have at least 2 different eigenvalues. Yeah, and so, for example, if we take any one of these, say, okay, so why there is an eigenvalue of T0 of the field F, since F, this T0 is at least half triangularizable. Yeah. Half triangularizable. This implies that there exists an eigenvalue, say, C0 of T0, and also in the field F. Okay. So, and the corresponding eigenvector V, such that T0 is 0 just equals C0 is 0. Okay. Then we just consider the one-dimensional space spanned by this vector V0 over the field F. Okay. Okay, sorry. We should consider instead of this, but the eigen subspace of C0 of 0, which is a collection of the vector V, such that TB equals C0V. Okay. So this simply means that W is not a zero space. Yeah, since it means that it does have an eigenvector here. And since T0 has at least 2 different eigenvalues, W is not the whole one. Okay. And since all linear transformations in the family fancy A commute with T0, W is also fancy A invariant. Okay. So actually, as before in our Museum problem number 4, we again descend our problem into a non-trivial invariant subspace W. Okay. So if in the case 1, our T0 is diagonalizable over F. It means that T0 can be decomposed into a direct sum of its subspaces VC. Okay, then we just do induction on each even subspaces of VC. Okay. So the proof will be clear. Okay. Then in the second statement, we may write T0 on a special basis, which consists of basis of VC0 first and the quotient basis of V modulo V0 next. So T0 will be of the block upper triangular form. This is V C0, and this corresponds to V quotient V C0. Yeah. And actually, all linear transformations in the this family A is of this form. Okay. Then we do induction on V C0 and the quotient space V modulo V C0. Yeah. So the proof is done. Okay. So I basically explained that for a commuting family of linear transformations, if each one in the family is diagonalizable or upper triangularizable, then they can be simultaneously put into the diagonal form or the upper triangular form. Okay. That's our basic observation. Now, I would like to give you some simple corollary of this proposition. Okay. Okay. You may also put it as an exercise if you like. Okay. So, for example, if you work over an algebraically closed field, say the field of complex numbers, then automatically each linear transformation is upper triangularizable. So means that if f is a commuting RE, then this family A can be simultaneously upper triangularizable. Okay. And what about if we work over a non-algebraically closed field, say the field of real numbers? Then in this case, we cannot expect that the family is simultaneous upper triangularizable, since real linear transformation may not have its eigenvalue over the field of real numbers. But of course, it will have a complex conjugate. So at least we can make it block upper triangular, and each diagonal block has order less or equal to 2. Simultaneously block upper triangular. Where each block on the diagonal has order not exceeding 2. Okay. You may see this as a simple corollary of our proposition. Okay. And actually, using the technique here, we find a non-trivial invariant substituted under the action of all linear transformation in this family. We prove more simple result, more general result. Okay. So, do you have any question about this? Yeah. No question. Let's continue. So I will also give you an exercise. For example, we take two. So for example, we may lose some conditions in the statement 2 here. For example, I mean this direction is only holds for in this direction. So I will give you some other condition rather than commuting family. See, if T and S are two linear transformations over C and satisfy either their composition is 0 or the rank of their commutator is smaller than 1, then T and S can be simultaneously upper triangular algebra. When we see that under this condition, this commuting family, we don't need such a strong condition. And do you have any other examples?
Family of 3 by 3 upper triangle matrix.
Yeah, that's a great one. Yeah, we also have an example. Okay. Bohan just means that if we take A to be the matrix form, see, the strictly upper triangular matrix, and the order is 3, then they are already of the simultaneous upper triangular form, but of course, this is not a commuting family. Agree. So, these are the exercise I want you to solve after this topic, and in the end, I would like to answer the problem that Bohan raised in the beginning of the topic. So, why should we consider the kernel or the image of a linear transformation when encountering these commuting relations? Okay, and I would like to answer using the following proposition. Okay, say that T be a linear transformation over any field F, and W be a T invariant subspace. Then, our conclusion is rather strong. There exists two linear transformations S1, S2, such that they both commute with T, and the composition of S1 and S2 is 0. And the most important one is that W equals the kernel of S1, also equals the image of S2. Okay. So this proposition simply means that if you consider a T-invariant subspace, it can always be written as a kernel of another linear transformation which commutes with T, and also it can be written as the image of another transformation which commutes with T. Okay, you see this proposition is very strong. I would like to give you an explicit construction of such S1 and S2. So, since W is T invariant, we may find a basis of V such that T is of the blocked upper triangular form. So, under a suitable basis, we may represent all these linear transformations as in the matrix form. Say T represented by and here we want to write it explicitly. Say equals A11 on the left upper corner, A12, A22, where A11 is a K by K matrix, and A22 is a N minus K times N minus K matrix. Okay. And our W is just the first one. Yeah. Just the K column. So let's recall the solution is that any matrix can be similar to its transpose of any field. Say there exists P in G of NF such that P inverse AP equals A transpose, and also P1 in G of KF is that P1 AP1 AP1 inverse AP1 is A1 transpose, and P2 in G of minus KF is that P2 inverse AP2 equals A2 transpose. Okay. Then we simply notice that A times this matrix, raw matrix, equals to the raw matrix times its transpose. And the same applies to P2. Say A transpose times this matrix by P2 equals this matrix times A. Okay. So finally, it suffices to write B as P times this matrix by P2, and C will be this matrix by P1 times P inverse. Okay. So this direct construction of such commuting linear transformations with T. And this is the end of our topic. Thank you for listening.